There's another setting on all your spectrometers, and that is a question of how long do you accumulate, or how many scans do you do. Sometimes you do multiple scans to do some signal averaging. And the takeaway here, so this is, for instance, the same spectrum taken with a one scan, which is down here. You can see it's very noisy. But instead, you can do 4, 16, 64, or 256 scans, which of course takes 256 times longer. But you can see the more scans you take, the better the signal to noise. And the mathematics of this works out that this signal to noise, here's the noise, the size of the or the width of this line that you're seeing here, this noise, that the signal to noise goes as the number of scans, or it's the square root, sorry, of the number of scans. So if you take 16 scans, right, that's going to have, the square root of 16 is 4. It's going to have 4 times better signal to noise. So this size here, which looks like whatever that size is going to be about 1/4 as much here. All right, and it's important to remember that it goes as the square root. It's not equal to. So if you measure it 256 times, this isn't 256 times smaller. It's the square root of 256 times longer. And this is important to know because sometimes you need better signal to noise, and you have to figure out, can you even do it in that 8-hour shift that you're working or whatever, as long as the spectrometer is stable. All right, so there is some limitation to how long you want to average. Okay, so far, so now you have a trade-off now when you're determining signal noise, is to determine which cuvette you're going to use to make sure it has as much transmission, what light source to use, right? Because there can be a choice of light sources, some of them having more light at certain wavelength ranges, which detector to use, which grating to use, what to set the slits at, right? And how fast or how long to average, right? So you can either scan or make multiple scans or just scan slowly. Okay, so far we've discussed transmission and fluorescence measurements, which are what these kinds of spectrometers are used for. But what about emission? Atomic emission, for instance. You may run into atomic emission spectroscopies. In fact, you may have seen this in your Chem 121 lab. This is a Bunsen burner, which you all know what Bunsen burners are, and there's a flame, right? You have methane gas coming in here, the same stuff that you burn at home if you have a gas stove, and you've got this flame. And if you were to somehow introduce some chemical, like some sodium or potassium or something, you would change the color of the flame because you see characteristic colors coming from different elements, mostly metallic elements. You don't get, or at least in the visible, you don't get much from things like water itself or the methane for that matter. But these are not what's used in modern high resolution atomic emission spectrometers. What are used is something called inductively coupled plasma emission spectrometers, all right, or ICP, inductively coupled plasma. And what this is here it's showing you a coil of wire. There's a coil of wire going around where this sample is going to burn, right? The sample's coming in here. The sample is coming in as a liquid, so you have a beaker with your sample in it, so whatever that is, and it's got some usually metals in that dissolved in there, right? And you have some little pump that's sucking it out and slowly releasing it as a little spray, right, into here, and at a very constant rate, right? Because you don't want this to be a noisy situation. So you're introducing this spray, and then on the outside here, you're introducing a lot of argon gas, right? Which an inert gas is not going to get too involved in this, and the spectrum from argon is not going to be interfering in the visible or where you're looking. But the flame that you get here comes from the fact that this coil is connected to an RF, radio frequency power source, and you're pumping power into this thing, like kilowatts of power, lots of power, enough that you break down, you cause a plasma to form, like you have in a fluorescent light. So there's electrons flying around, there are ions flying around, everything's bumping into each other. And this thing, you can see here, the temperatures, 10,000 Kelvin down here, and other temperatures up here. And what you do is you take you have a spectrometer and you focus the entrance slit at this cone of burning light, right? And you can then see emission coming from different atoms. And this ICP, because it's so hot, right? It's twice as hot as this Bunsen burner. You know, it's many times more expensive, but it's twice as hot. It's much more stable. There's less interference, and you get more signal out of it. So this is what you'll see in a lab, like when they're measuring water quality. The local water district has to measure to make sure there isn't too much in your drinking water, things like that. They'll use this kind of a spectrometer. It can measure things down in the parts per trillion range, of metals dissolved in water. I had a chance to use a spectrometer like this a long time ago. I was making superconductors, high temperature superconductors, which were made out of the yttrium, barium, copper. They were yttrium, barium, copper oxides. There were some others too, but this was the first one. And these were discovered back in the early 1990s. And I was making thin films of these. All right, so I had a target, and then I had a way of making a film. And I'd make a film of this. And I mean, a film, it was very thin. You know, it was only less than a micron thick. And it may be on a 1-inch disc. I'd deposit onto a 1-inch substrate. And I needed to know what was the ratio of the yttrium to barium to copper, because it's supposed to be 1, 2, 3, but I could vary things, so it wasn't always 1, 2, 3. Right? So you had to tune it in. And what you would do is, or what I did, was I took that little 1-inch disc with the thin film on it, and I dissolved it with nitric acid, a little bit of nitric acid, into a small amount of water, right? And I introduced it into the ICP spectrometer, and then I would scan the wavelengths. Again, you have a very sensitive monochrometer there, but I knew where the strong lines were for yttrium, barium, and copper. So I would go over to the yttrium line and measure it, go over to the barium line, measure it, go over to the copper line and measure it. So I would see emission from 3 different, and there was no interference, because remember, atomic emission lines are very narrow. And if you pick the right ones, there's nothing else nearby. Because after all, the only thing that should have been in there was yttrium, barium, copper, some water, other oxygen from here also, and maybe some sodium or something that was in the water or in the glassware that's hard to get rid of. And then to know, so that I would see emission lines, and then of course I'd had to calibrate this. And to do that, you would buy from a vendor a bottle of something that they would tell you that was, say, 1 part per 1,000 or something like that of yttrium in water, yttrium oxide dissolved in water, or barium in water. So I had 3 different calibration sources, and I would dilute those down so that they were similar to what I was going to be measuring, and then I would do a separate calibration run to see how, with known quantities, known concentrations of yttrium, barium, or copper in the water. And again, it doesn't matter what the form is. Once they get into the plasma, whether it's an ion, a +1 ion, or +1, it doesn't matter. Everything gets completely busted apart by that hot plasma and looks the same. It doesn't really matter its history anymore. Okay, so that's atomic emission spectroscopy. Now let's switch gears to radio waves. What are radio waves used for in spectroscopy? And that turns out to be NMR, nuclear magnetic resonance spectroscopy. And what's involved here is the spin of the nuclei. And you probably haven't talked about this. It's not taught Chem 121, but you talked about electron spin. Well, it's similar to electron spin, but it's nuclear spin. So it's the nucleus itself can have a spin. It doesn't always have a spin. Turns out some nuclei have a spin and some don't. So you have to pick a nuclei that has a spin, and then normally, and then you would have a spin up and a spin down, right? Just as you had electrons, you had spin up and spin down. And normally those 2 states, spin up and spin down, are degenerate, meaning they have the same energy. So you can't really have a transition between the two of them. But if you put them in a magnetic field, that separates the energies of the spin up and the spin down, depending on the direction that the magnet is pointing. So you do that. You put your sample, right, in a tube, a glass tube, and you put it in between the poles of a magnet, and a very strong magnet. And then you have a radio frequency source, because the splitting is not very large. It's not as much as the visible or even the infrared. It's way out in the radio range. And the way the older spectrometers worked was you'd have this radio frequency transmitter and then detector. So there'd be one coil as the emitter and one as the detector. And then you would slowly scan the magnetic field, right, by controlling this iron magnet with the way you control it. It's an electromagnet. And when you got to just the right magnetic field that your sample was absorbing, you would see something in your spectrum. You would see a peak in your spectrum. Anyways, that's the old way they worked. That's not exactly how they work now. First of all, the better resolution you have, the higher the field, or I should say it the other way around. The higher the field, the more the resolution. Right? It's easier to see your spectrum. So modern spectrometers want to use the biggest honking magnetic field that they can. And those turn out to be superconducting magnets, big magnets. And they don't vary the magnetic field. It turns out there's a more efficient way of doing it, and that is you keep the field fixed, very, very parallel, very fixed at as strong a field as you can, and then you don't scan the wavelength of the RF signal. You actually give it a pulse. You give it a pulse of wavelength, and then you listen to the ringing. So you pulse it. There's a pulsing scheme, they call it. It's actually a scheme with different time delays. You pulse it, and then you watch the ringing. And like FTIR, you get the time dependence of the signal, and then you take the Fourier transform of that to get your spectrum. But the end result is the same, right? The end result is the same. So that's NMR, nuclear magnetic resonance spectroscopy. Now, I said that several nuclei or different nuclei can have a nuclear spin. It turns out that this technique is used almost exclusively by organic chemists, because most of the time the sample is relatively pure. The chemist has made the sample, purified it, and wants to see exactly what it is, right? And so then you dissolve it in a fluid and you put it into a tube inside the spectrometer, and 99% of the time, what they're looking at is hydrogen, right? It's the spin of hydrogen that they're looking at. There are some other spins like phosphorus that show us that have a spin that you can. A lot of nuclei don't have a spin, but hydrogen is what they're looking at. And we have one of these at Channel Islands. If you're on the first floor of, as you come in the door of Aliso Hall, and you walk around there in the lobby, there's a window looking into this lab, and this is what it looks like. Right? And this here is this huge dewar. I mean, this is a step ladder, so you can get an idea of how big it is. So it looks like this thing's like 4 or 5 feet in diameter, and it's as tall as a person. Right? It only comes down to here, and then there's other equipment coming in from underneath, and here are tubes coming out the top. This is the magnet part, the superconducting magnet. Now, superconducting magnets, first of all, have to be kept, this type of superconductor, very cold. So it involves liquid helium, which exists at about 4 Kelvin, right? 4 Kelvin, and then and it's expensive, and you want to keep it in there as long as possible because it eventually will evaporate or it'll boil off. And so they use liquid nitrogen, a jacket of liquid nitrogen around it, just so that the liquid helium doesn't disappear too fast. So it's got helium and nitrogen, liquid helium and liquid nitrogen. And the spectrometer is measured by the size of the field, the size of the magnet in terms of its strength, is measured in the frequency that hydrogen, because that's what everybody's using it for, of the hydrogen transition. And so I asked somebody, and it turns out the Channel Islands spectrometer that we have down there on Eliso Hall is a 500 megahertz spectrometer, which means hydrogen resonance in that magnetic fields is at 500 megahertz, which I found kind of interesting because I did some research when I was an undergraduate using NMR spectroscopy, and at that time we had a 220 megahertz magnet. So it's more than doubled in the years since the 1970s when I did the work that I did. Okay, so that's a big NMR spectrometer. Now, what size sample do you stick into this spectrometer? Turns out they're tiny little tubes. They're almost universally 5 millimeter diameter tubes. They're kind of long, and you don't even use the whole thing, but I mean, that's the sweet spot in there is smaller than that. But so those are NMR tubes. And again, I mentioned it's mostly used by organic chemists, or almost exclusively used by organic chemists. But there's another technology that's related to NMR that's used in medical diagnostics, and that is magnetic resonance imaging. Right, so don't want you to get confused. MRI, they changed the lettering. They wanted to get nuclear out of there because it made people who were being slid into this thing a little nervous when they heard nuclear. So they call it magnetic resonance imaging. And what it is, it's just an NMR, and of course it's looking for hydrogen, but it's doing 3D mapping. So by way of looking at different coils around there and all, it's essentially the same thing, but they're not trying to look at, as we'll see, the spectrum. They're just trying to see how much hydrogen there is in your body in different places. So, and I don't know too much about the medicine or anatomy of humans, but what they must be measuring is the density of hydrogen in different parts of the body. So presumably there's different amounts of hydrogen in, say, fat versus bone versus blood or whatever it is they're looking at, right? So that's what they do with a MRI. Okay, but let's go back to how organic chemists use nuclear magnetic resonance. Here's the spectrum here on the left. This is the I guess theoretical spectrum, and over here is the actual spectrum, which is essentially the same thing, from ethanol. So it's ethanol. And what you see is you're seeing the hydrogens. Now, first of all, let's look at what the units are. ppm, parts per million. And what this is, there's some theoretical zero, which would be where hydrogen would be if it wasn't shifted. And then different hydrogens in different parts of in this case, ethanol. There's one hydrogen which is attached to the oxygen. There are two hydrogens on this middle carbon, and three hydrogens on this end carbon. And they appear in different places. So the one on the oxygen gives you a signal here, and the ones in the middle are over here, and the ones at the methyl group at the end, they're over here. And this shift, you can see it's 1, 2, 3, 4 parts per million. And the reason they do it as parts per million is because this is parts per million shift from the 500 megahertz. So you can think of 0 as, say, being 500 megahertz, and this is 501, 502, 503, 500, it's 1 part per million. 1 part per million would be, well, if it's megahertz is 100 hertz, so is a million already. So 500 megahertz, so 1 would be 500 hertz, 500 hertz separation, and this would be 1,000 hertz, 1,500 hertz. And they do this because not everybody has the same size magnet, so that you don't have to normalize everybody's different spectrometers. This spectrum may have been taken on a 100 megahertz spectrometer, but as long as you put it in parts per million, you can compare it, and they can put them in books so you can see what different things should look like. Now, what is this shift caused by? Now, you'll have to take organic chemistry, which I took a long time ago and haven't used it since, but this tells you something about how many electrons are around the hydrogen, because these electrons around the hydrogen, and of course every element in a molecule has, except unless it's ionized hydrogen, has some electrons around it, and those electrons help to shield the magnetic field so that the hydrogen doesn't see that full 500 megahertz because it's got some shielding. And depending on how much the electrons have been pulled away by the nuclei that are near them. So for instance, oxygen tends to pull things away. Then they become more exposed. So the ones that seem to have the largest shift, it turns out here, and I can't tell you why because I've been so while since I've done this, but that's why they have different shifts. It has to do with if you had something like, say, methane, propane, something that had very little shift at all, then all the signals would be down here between 0 and 1, right? Once you start putting oxygen, bromine, chlorine in there, things get shifted much further away. The other thing you see is there's some splitting going on here, which gets rather confusing. So for instance, this hydrogen here, this red one on the oxygen, only has a single peak, or you can hardly see any splitting, very narrow splitting if there is any, right? Whereas this carbon here, which has 2 hydrogens, it has 4 peaks, and they're not a 1 to 1 to 1 to 1. It looks like the middle ones are broader, but there are 4 peaks. And it turns out, this I recall, that you have 4 peaks here because it has 3 nearest neighbors. This hydrogen here has 3 blue neighbors near it. So those 3 blue neighbors cause both of these hydrogens, which are identical, so that they would otherwise be right on top of each other, to split into 4. Whereas these hydrogens here on the end group, right, have 2 neighbors, so they split into 3. It's pretty bizarre, and you'll have to wait until you take organic chemistry to figure out exactly how this all works out. But it helps you assign what hydrogens are on what molecules, because you can look at all these things. And you can see as things start to get cramped together, you want as much resolution as you can find. Okay, so I think that about covers what I wanted to say about spectroscopy. So again, we talked about what spectrometers, why they're important, right, in most modern laboratories, and you will find them in most laboratories that you work in. And we talked about different types of spectroscopies in different regions of the electromagnetic spectrum, right, whether they be in the radio waves or visible or the infrared. They probe different aspects of the sample. We talked about different sources, right, that you would have. We talked about different monochrometers. We talked about different cuvettes that you would use for your sample. We talked about, or windows, different detectors that you would have for different spectrometers. We talked about different units which are used in different wavelength ranges. And we learned why atomic absorption and emission are line sources, whereas when you get to molecules, then the absorption and emission tend to be broader, right? Especially if you're looking in the visible, right? Our infrared, things get to be broad because of all the vibration and rotation that's going on. We talked about fluorescence, which is a 2-step process, right? Remember, the emission is always at longer wavelength than the absorption part was. Remember, because the energy comes in on one photon, and then there's some, it can drop down to a lower energy state with a non-radiative method, and then it emits at a lower energy, longer wavelength. And this can be a very sensitive technique. We talked about calibrations, the need for calibrations and how they're done, about filters. We talked about Fourier transform infrared and why that's commonly used, what it is, inductively coupled plasma emission, and finally NMR. So here's a list of some of the different types of spectroscopies that we talked about. I didn't get into all of them. We didn't talk about Raman or necessarily or laser spectroscopy. And then there are some other spectroscopies that we didn't talk about at all, which don't necessarily only involve light. So we had mass spectrometry, or spectroscopy, which involves figuring out the mass of your compound, right, by breaking it down in the gas phase and measuring it that way. There's secondary ion mass spectrometry, which is used for solids. So you remove some material from a solid surface and see what the mass of that was. X-ray photoelectron spectroscopy, Auger electron, and X-ray diffraction to look at crystals, to see the spacings in crystals. So it's a very rich field, spectroscopy. There are whole chemistry courses that are taught about spectroscopy at some universities, and maybe there are even at Channel Islands in some years. And I've used most of these spectroscopies at one point or another in my career. So if after you leave Channel Islands you find yourself in a lab that uses one of these spectroscopies or more than one of these spectroscopies, don't treat it as just a black box, right? Some instrument that you shove your sample in and out comes a spectrum, right? You should get to know the instrument, get to know the various settings, get to know that type of spectroscopy and what it's used for. Try to understand that tool, that spectrometer, what it can do, what it can't do, and what improvements could be made to it that you might even be able to suggest to do a better job, to make it more sensitive, for instance. You might be able to use this information to impress your colleagues or your customers or even your boss, with this kind of information. Okay, thank you for your attention.